So we're doing gas laws, which I keep referring to. Brown pen. And the big thing with gas laws is you can calculate. So there's these variables, PV, T, and N. And I picked the wrong marker. And this is the key. Once you get the 4 variables down, it's all just algebra, which is really basic. So P is pressure. And pressure, with each of these variables, you have to also know, especially from a chemist's viewpoint, because it is chemistry, pressure is collisions. So it's atoms or molecules colliding. So in physics, you learn that pressure is force, right? It's force in an area. And so that's the idea here, is the atoms are colliding. So you're going to see when we get to the math on the next page that I keep asking, does the answer make sense? So if the pressure goes up, that means there's more collisions of the particles of the atoms and molecules. And then the units we've kind of seen a little bit is ATM, which stands for atmospheres. And 1 ATM is considered standard. The other unit that you'll see me using, and we've already used on the homework set you guys did today, is 760 millimeters of mercury. And what that is if you had a barometer. So that guy in the middle of the page, if you have notes, he's holding one of the first barometers, is this tube, and at the bottom, what they had would be mercury. And as the air would push on the mercury, mercury's a liquid, that this would rise up the column depending on how much pressure was pushing down. And if it's a perfect day, this would rise 760 millimeters. And so if we were in lab, that's one of the things you get to do is, actually we now have an automatic one. We're not allowed to have a mercury one. So these, we're going to be converting between them. And so that was a question you had to ask me, Erin. 1 ATM is 760 millimeters of mercury. All right. The other unit for millimeters of mercury is 760 is also 760 torr. And I'm pretty sure I mentioned that last week. But torr is an abbreviation and in honor of Torricelli. I have a little thing about him at the bottom of the page. He was actually a disciple of Galileo. So I guess if you're as brilliant as Galileo, you get to have disciples. And he worked a lot. He was the one who made the first mercury barometer and did measurements of air pressure and stuff. And so that's why the unit is named after him. He didn't name it after himself. All right, V, it is a capital V, is for volume. And volume is the space occupied. And I think I spelled that right. So it's how much space the gas is taking up. So this room would be the whole volume of the room. So that's one of the things that's special about gases, is they always occupy all the space they can. As opposed to a solid or liquid, which have a fixed volume, a gas will expand or contract to fit whatever space it's in. And the units for volume, we know we're going to use usually liters. You could also use gases take up a lot of space, so we usually don't do milliliters. You could. Milliliter was the same as a cubic centimeter. And a liter, by the way, is the same as a cubic decimeter. So sometimes that's handy to know when you're doing homework, but we're going to mostly be in liters. And I'll go through that as we're doing the problems. Capital T is for temperature. And temperature, I talk about, is jiggles. So it's kinetic energy, which is movement, and I talk about it as jiggles. So as the temperature goes up, everything's jiggling more and giggling and wiggling and all that stuff. So there is only one unit you can use for temperature for gases. And this is probably the most missed thing by students, and it is a capital K, which stands for Kelvin. So Lord Kelvin, so he was English. Kelvin, so Celsius was French, and Celsius came up with his scale based on water. So 0 degrees Celsius was the freezing point of water, and 100 degrees is the boiling point of water. So it makes perfect sense. And then Fahrenheit was before him, and I can't remember the history behind his scale. But Celsius was from France, and so Kelvin was from the United Kingdom, from England. And he said, is there a point where you have 0 Kelvin, where you have no movement of particles? And that was called absolute zero. So 0 Kelvin, right over here, I keep forgetting. So that's a 0 Kelvin, not okay. 0 Kelvin is when there is no movement. So there's no jiggles. So if you had a perfect crystal, so like the necklace I wear, which, and we got it down to 0 Kelvin, there would be no vibrations, nothing. There would be complete stillness. And so the thing that's interesting is they actually have gone to below 0 Kelvin. And they can get really close to it, but they can never actually be at 0 Kelvin. So we will never see a negative temperature in Kelvin. The trick is more converting between Kelvin and Celsius. So 0 Kelvin is negative 273 degrees Celsius. So it's really cold. So usually what we're going to do tonight usually takes me 3 hours, because I usually do a whole bunch of demos because I have liquid nitrogen available. So if I am videotaping this wrong and have to do this whole thing over, then I guess I'll get to do my demos. But I had a brilliant idea, and I realized you guys are going to do the demos because you're all at home and you have nothing to do. And there's like a zillion gas law demos online. They're really cool and really fun. You don't have to. Your next lab, there's going to be 5 options, and you have to pick 3 of the 5 to do. But I figured, especially those of you who are here tonight, that you would probably really enjoy doing a demo. So you can either videotape yourself or you can actually do it live for us on Zoom. But yeah, there's a lot of really fun demos. So temperature, I can lower, you can also raise the temperature like by heating it and stuff. So that's what a lot of them do. You can do ones where you make it really cold. So even though you guys don't have liquid nitrogen, you can actually get dry ice at every store now. You'll probably all get carded because you have to be 18. And so if you're male, they're going to ask to see your ID. They actually ask for my ID, but because young boys will take pieces of dry ice and put them in a bottle and make the bottle blow up. But you can do ones where you make a dry ice bath and just make it really cold, and you can do some really cool demos with that. All right, so temperature has to do with jiggles and giggles. Volume is the space occupied. Pressure is the atoms. And so this is chemistry. So the N is our favorite unit in this class, which is moles. So, which is measuring the number of molecules. So again, remember, you would have to use Avogadro's number to convert between moles and molecules, but it's a little n. Molecules, of course, would be Avogadro's number is the capital N with the subscript A. But it's a measurement whenever we solve for N of moles. So when you do this in physics, you spend a lot of time talking about pressure and the ability to do work and stuff. In chemistry, you can see where we're going to be going. We're going to get to balanced equations and stuff. And this is actually where chemistry came out of, was gas laws, because again, the demos are so simple to do that a lot of the original studies were done with gases. At the top of the page, I skipped this. It said, what is a gas? And so it was a gentleman who was German. And when you say the word chaos, so gas actually comes from the word chaos. And chaos just means chaos. It's kind of like what was going on in this world a month ago when, you know, and even sometimes now when you go to the store. So everything was chaos. And if you can speak with like a really good German accent where you're talking from your throat and you say chaos, like with that really deep, the hard CH, it sounds like gas. And so chaos means gas. And that is because they're always moving, always moving. There is nothing static about these. So they're always jiggling and giggling. And the other thing about a gas, why they're always moving, is they have weak IMF. So that was something I talked about last week. And so that's an advantage of me changing the order, because you guys already have kind of the idea of intermolecular forces, and that's what makes liquids special, is they have the intermolecular forces so they can move around. What makes gases special is they have so many jiggles and giggles, they have enough kinetic energy that they don't have the attractive forces, so they're just going all over the space, all over the place. And so that's why they're special, and there's that little picture there. At the bottom of the page is the idea of a vacuum, because pressure is usually, of these, the one that most students don't know really what it is, and based on the questions that several people were asking me. And so I was going to talk about pressure unless somebody has a question on one of the other ones. I'll just keep going. All right. So one of the things with pressure, and it's actually another demo, I might still do it, how long doesn't erase so well, is if you make a vacuum, and you've all seen some kind of space movie, but a vacuum means that you suck out the air. So I'm not talking about like a vacuum cleaner, like you're cleaning the floor and stuff. So a vacuum, so space, in space, there's very few particles, right? So there's so much space in between all the atoms that hydrogen actually doesn't exist as a diatomic, because they never come in close enough contact with another hydrogen atom. But so that's the vacuum of space. Whenever there's, if you see in the sci-fi movies, whenever the spaceship like breaks, people get sucked out, because outside there's no pressure, and inside the air pushes them out. And so that's the thing at the bottom. And actually in lab, you guys have done suction filtration, and that is where we use a vacuum, and it pulls all the air out of the tubes, and it creates a vacuum that will suck stuff through. And so the picture is, this is more kind of, I mean, physics and chemistry is really the same thing. But in the physics lab, he has this, and you could probably Google it and see this demo. But these are two steel balls, and they have a way to suck the air out. And so they're separate, and when they put them together and you suck the air out, they stay together. There's no way, you can't pull them apart. And so that's a picture of this guy and who first made it. And those are horses on each side. So the horses were pulling in each direction. So I think they had like a team of 4 horses on each side of this, and the horses could not pull it apart, because if there's no air inside, there's nothing to push it apart. And then they did something really weird. They put a candle inside, and of course the candle won't burn, but then they put a dog inside, and the dog died because there was no air. I know, I was like, this was inhumane. This was back like in 1650. But anyway, that's the idea of a vacuum. And that's the demo I usually do for our first law. So I'll explain what the demos are, but I'm hopeful you guys will come up with some really fun demos. So I'm on page, mine says page 14. I don't know what page numbers. I've kind of given up on page numbers because everything seems to be doing funny page numbers. Oh, I wonder if my other eraser is there. All right, so we're going to walk through the different laws. And usually at this point, somebody says, well, do we need to know these? And it doesn't really matter. The things that you absolutely need to know, they eventually show up, and I have them highlighted, and I'll highlight them on the board as best I can. But this walks through 4 different laws by pretty famous chemists that gets us to the ideal gas law. And so the first one is called Boyle's law. And there's a beautiful picture of Boyle. And I don't know if that's a wig or if he just really had that much hair. But he is considered one of the founding fathers of chemistry. So like Galileo is for physics, what Galileo and Robert Boyle did is they both said the importance of recording your data. and they both are alive about the same time, which is when there's a lot of things happening with philosophy and stuff. But he was very big into, you need to take really good notes. So why you guys had notebooks in lab when we did do lab. What he studied was relationship between pressure and volume. So we're going to walk through just two variables at a time and comparing them. And so his lab, the story is that he had a 17-foot tube, and he would find if he changed the amount of mercury that was in there, it would change the amount of air and vice versa. There's a picture there. Basically, if you increase the pressure, so if you had a cylinder here that has a fixed amount, it's closed, and has a fixed amount of air in there. So the air is running into the sides, running into each other, and so that creates pressure, which is collisions. And so it has a certain volume. So to increase the pressure so that they're colliding more, you can just decrease the volume, or vice versa. It doesn't really matter. So if they're occupying less space, you're going to see many more collisions, is the idea. So these are always inversely related. When one goes up, one goes down. And so when things are inversely related, the law comes out that if you take a condition of pressure and volume, you will always, multiplying them, you will always get a second set, P2 times V2 will always equal P1 times V1. So in Europe, they don't actually call it Boyle's law. They call it Marat's law, because Boyle forgot in his paper to state something, which is for this to be true, temperature has to be constant. So really temperature in moles. This is before moles, though. This is like 100 years before Avogadro. So temperature in moles must be constant. So whenever we only look at two variables, you'll often see that, and sometimes I just leave it out, that will say, oh, these other ones are constant, meaning we're just going to ignore them. But if we change the temperature and things start having more and more jiggles, well, they're going to collide more often. So that will definitely affect the pressure. And also if we added more stuff into there, like a balloon, that's going to create more collisions. So that's actually very important. And it was an oversight on his part. So there's a picture there of what are called peeps. So at Easter time, there are these little marshmallow bunnies. And so the demo that I get to do is I put them in a flask and then I hook it up to the air. I can try and draw it. So we put them in a flask, and so there are all these cute little marshmallow guys, right? So we'll just put 5 marshmallows. And what happens is if I create a vacuum, all the air gets sucked out into the vacuum. And so if there's no more air in here, there's no more air pushing down on the marshmallows. And what happens is the marshmallows get really big. Marshmallows are actually really awesome for doing gas law demos because they're basically filled with air. And so they get huge. And then when I break the vacuum and the air comes back in, the air is going to push them down, and they all shrivel up really small, and everybody moans and feels so bad for them. But we're going to go ahead and do the first problem, and this will just show you how to do all the problems. And gas laws, again, are pretty straightforward and pretty, I think they're pretty easy, because as long as you identify all the pieces. So my recommendation, you can always underline what's given in the problem, or you can make a list. So I'm going to make a list. So it says we have 2.5 liters of hydrogen. And so that's obviously a volume. And it's the first volume given, so I say volume 1, and it has a pressure of 5 atms. So these two go together because they're in the same sentence, 2.5 liters at 5 atms. And then it asks what volume will it occupy. So V2 is my question mark, and it gives me a new pressure of 745 torr. Now, you're going to see me abbreviate torr as just a little t. I've seen that in many places, so you can absolutely, or you can write TORR. It's always lowercase letters. So you only have pressures and volume. So make your list, state the gas law. So this is not going to be factor label. This is going to be algebra. So you always state with the variables first what you're using, and then you just fill in and solve. I don't have to see all the rearranging, but you can do it. So we would fill in that we have 5 ATMs. Oh, so sorry. So there's 2 ways you can do this step. You can fill in and then rearrange, or I'm going to actually rearrange first. My recommendation, and I have seen my top math students who are like in algebra 29 or whatever, that they end up screwing up gas laws because they rearrange everything in their head and they end up doing it wrong. So always state the gas law how it is and then rearrange. So this is a trick for those of you who are not fans of algebra, is circle the variable you're solving for. It's actually, algebra was taught to you back in kindergarten. They just didn't use the fancy name algebra. And so you're going to divide by the P2. Again, you don't have to show this, but it is my top math students who will flip this the wrong way. So always write out the equation with the variables and then rearrange, and then you plug in. And the biggest point for all of you, most of you know me, so you know that you have to show your units. So the number means nothing without the units. And the reason you need to show your units, making sure you label, put everything in the right place, is you can see our units are not going to cancel out because this was in ATMs and this was in TOR. So you could change your TOR to ATMs over here, and that's fine. I think most of you are pretty good with math skills. You can also change it here where you would just say, okay, there's 760 TOR is 1 ATM. Yeah, there's actually a really cool demo. I'm hoping somebody will try it, where you can suck an egg into, like I do it in lab with a flask, but not with a vacuum. So you have to have a hard-boiled egg, not a raw egg because that would make a mess, but a hard-boiled egg, and you peel it, and there's a trick to get it sucked into a glass bottle. There's a couple ways to get it in there, and that all does with gas laws. So again, just Google it, and there's some really cool demos out there. Anyway, so you would plug that in, and you would solve, and we're going to end up with 2 sig figs. So you get 13 liters. So that's the idea, that they're all going to be similar to this. So you're just, if you make your list, you state your formula, you plug in, and you solve. That's all there is to it. And really, the students who take that moment to make their list and to state their formula, they get this all right. And then you have a lot of breathing room going into, because I know where we're going next. And you want to ace this part. So the IMFs, the solids, they really weren't that bad. So they're all looking very similar. And so you want that breathing room, because we get to that point in the term where everybody, you start having stuff from all your classes. As I mentioned, I love asking this question that's at the bottom of the page that says, does your answer make sense? And this is where we would go back over here. And so 760 is standard pressure. So this is less than 1 ATM. So just looking at this, my P2 is a decrease in pressure. So my volume should definitely increase. So if pressure goes down, volume should go up. And so you go, yeah, pressure went down, so my volume went up. You will get a point or two taken off. So you would have to say pressure decreases, meaning there are fewer collisions. And the only way there could be fewer collisions in a closed container I like writing with chalk better. Just had to get that complaint out there. All right, so you have fewer collisions in a closed container, meaning we're not adding, we're not taking away, we're not allowing stuff to escape, is that you must have more space. So somehow it expanded. And there's also the jiggles didn't change, the temperature didn't change. So when I ask you to explain it, you're telling me these are inversely related because of that reason. All right.
Dr. Sherpa?
Yep.
So anytime we're doing gas laws, we're always going to have to end with obviously our calculations, but also stating what goes up, what goes down, what increases, decreases, plus an explanation.
If it says, does your answer make sense? So when I post the next homework set and worksheet, you will see sometimes I ask that and sometimes I don't. On these first 2 pages, I ask that with every one of them, because when we're comparing 2 things, it's pretty easy to do that. So you will see it sometimes, but not all the time. And so only if I ask that. So yeah, really good question. Anybody else got a question? I think Joey's wrong. I think we're gonna have to do this whole thing up. All right, so we're on my next page, which says Charles' Law. And Charles' Law is, Charles was, by the way, Boyle's Law is how your lungs work. So a change in the pressure, your lungs expand, the pressure decreases, and so it's how everything will bind then, like to the oxygen binding to the hemoglobin and stuff. So Charles was a Frenchman, and it's when hot air ballooning became really popular. And so he did studies where he compared temperature and volume. And so a hot air balloon works because as you increase the temperature, you increase the jiggles and giggles and wiggles. So if everything's moving, jiggling and giggling and moving faster, it's gonna take up more space. And again, it's because pressure is constant. So keeping pressure constant and moles, that if you increase the temperature so you have more jiggles, the gas is going to have to take up more space if it's not colliding anymore. So these are a direct relationship. If one goes up, the other one goes up. And that's what that little picture there is trying to show you, that if you're heating it, the jiggles will make it go up. The other way you can do it, this is the cold balloon, that if you decrease the temperatures, this is where you do a cold bath. And it has to be really cold, so liquid nitrogen works really well. And you blow up a balloon and you pour the liquid and tie off the balloon so it has a fixed number of moles of air in there. You will actually shrink the balloon down to really tiny. So it's actually really fun to do that. All right. So the example. You have 0.50 liters of air. So that's our volume. And we're at 20 degrees Celsius. So that's V1 and T1. So these go together. And then it says, what's your new volume? So V2 is my question mark. And my new temperature is 37 degrees Celsius. So we only have volume and temperature. I forgot to give you the law that in the previous one, pressure and volume were inversely related. So it was P1 times V1. When they're directly related, it's actually a ratio of V1 over T1 equals V2 over T2. So if one goes up, the other one goes up. So it's written as a fraction. So this is going to be the formula we use. And then we're going to plug in except, so 0.50 liters would be V1. To move the T2 over, right, you would just multiply. So we cross multiply. So it would come out on top there. There was something I mentioned when I talked about temperature. You can never use Celsius. So Celsius, when he came up with the scale, it was purely based on the freezing point and boiling point of water, which is the most important substance for us. That this does not work with gases, because gases are all about chaos and movement. Kelvin, when he made his scale, he took into the idea of movement and kinetic energy. So you can never use Celsius. You always have to add the 273. I don't need to see this step. I usually just cross it out and automatically change it to Kelvin. Like this would be 293 Kelvin. So temperatures are going to be given to you in Celsius in the problems, and then you always change them to Kelvin. And we want to be careful because the T2 is going to go up here in the numerator, so the 310 Kelvin, and we're going to divide by the T1, which is the 293 Kelvin. You punch it in your calculator. This had 2 sig figs, so my answer is going to have 2 sig figs. So 0.53 liters. Now back to the question Janae asked. I do ask here, does your answer make sense? And so you would tell me, okay, my temperature increased. So if you increase the temperature, you have more wiggles, jiggles, giggles, kinetic energy, movement, whatever word you want to say. So there's more wiggles, so it's going to increase the volume. It's going to take up more space because you don't have any more collisions. So P is constant, meaning same collisions. So if it's still colliding the same, even though everything's wiggling, everything's wiggling and jiggling, and so it's like kids, as they start wiggling and jiggling, they're going to start running into things, so you've got to give them more space. So it's like, now one of the other things, so our volume did increase, it did not increase very much. So if you go back and look at the original numbers in the problem, in Celsius, it looks like the temperature doubles, but the volume barely changed. And the reason is Celsius does not work in gas laws. You have to always change to Kelvin. And when you do change to Kelvin, you can see the temperature change is not actually that much. And so the volume change is also not that much. Anyway, so that's Charles' law. The next one is Gay-Lussac's law. And
actually, before you erase the bottom, I was wondering, do you know how it says because P constant and then it's a little
same
bit
collisions, like, same number of collisions.
Oh, okay. All right, cool. Thank you.
So pressure is always about collisions. So if you keep the collisions the same, yeah. All right.
Hey, Dr. Sherpa.
Go ahead.
I don't know if this is like really far from what you're talking about, but I was just curious. In this situation where we're talking about gas laws and kinetic energy and releasing energy and stuff like that, would you ever apply like catabolic or anabolic to the situation?
I have to think about that.
Okay.
I know what you're asking. So probably not, because gas laws work when you're dealing with pure gas. And like a catabolic process is the breakdown of something. And that we're usually not talking about that in terms of a pure gas.
Gotcha. Okay.
Yeah, because like in metabolism, I mean, that's where I've heard the term catabolic and anabolic is with metabolism in biology, biochemistry and stuff, which isn't working with gases. And that's why this works. This does not work with liquids. This doesn't work with solids because they are not chaos. And it has to do with, because gases are always moving, because of their chaos, these hold true. So it's something I always joke about, that in physics they have all these laws because they just said they're laws, which is really what it is. I heard a really awesome talk today. I went down my own rabbit hole today, and he was saying that with sciences is you can explain everything, but you always ask for one grace card, which is a miracle. And so like with the Big Bang, he says, we can explain everything after the Big Bang. And so our miracle grace card is, oh, everything just suddenly existed. And if you think about it, it is. It's kind of a weird part about the Big Bang. Well, where did all that stuff come from? And so we can explain everything after it. It's a wonderful theory, but there's this miracle that has to happen first. But they don't call it that in science. All right, so Gay-Lussac, he compared temperature and pressure. So temperature is our wiggles, our giggles, our jiggles, our kinetic energy. So if you increase the giggles, but volume is constant. So volume in moles are constant. So again, it's a closed container. So it's not expanding or contracting. You're not adding any more. If everything's jiggling and wiggling more, you're going to have more collisions. So if you increase the temperature, you're going to always increase the pressure, and they always increase proportionately. And that's the thing that's really cool about gases, that they're like the greatest application of algebra. So this is going to be a ratio again. I'm just saying what I'm using. Yeah, we're solving. So P1 over T1 equals P2 over T2. And again, we're going to combine all these, and that will be the one. There's one that you can derive every single one of these from. But when I teach it, I always walk through the history that got us to that one overall encompassing equation that we use. Can solve anything we do with gases. So again, liquid nitrogen, we can do some really cool stuff. But you can do the same with dry ice. Just be really careful because it is really cold. And there's like a collapsing can demo that's really cool to do. So, all right. So the example is we have 4.0 liters of chlorine gas at STP. So I forgot to mention what STP was on the very first page. And STP stands for standard temperature and pressure. However, I did mention what standard pressure is. So standard pressure would be 1 atm or 760 millimeters of mercury or 760 torr. And standard temperature, this is the part that's really bizarre. Standard temperature is 0 degrees Celsius. I have no idea. Somebody declared standard temperature is 0 Celsius. Because usually 1 atm is like a day at the beach, right? We're at sea level. So 0 Celsius, it doesn't make sense. Because everything else you do in chemistry and physics, standard temperature is either 20 degrees or 25 degrees. But this would be 273 Kelvin. So sometimes I don't give numbers, I just say STP, and that would mean you have those two numbers. All right, so this would be our P1, that's our V1 is the 4 liters, and this is our T1. So those all go together. And then it says, what will the pressure of the gas be at 45 degrees? So T2 is 45 degrees, and it wants to know the pressure. And it doesn't mention volume, so we can ignore that fact. So we're just going to compare pressure and temperature, which means we're doing that formula up there. So P1 over T1 equals P2 over T2. So always write your little list, and then it will tell you which formula you want. I think it can be really helpful to circle the piece you want. That piece that I circled, the P2, has to end up isolated, has to end up by itself. That's the whole point of algebra. So the T2 we would multiply, so the T2 would end up on the top in the numerator on the other side, so it's cross multiplying. Something else to think about, and usually I don't have this problem in here, you can't have a temperature times a temperature. So one of the temperatures would be in the numerator, in this case the T2. And again, we have to change this to Kelvin. So 318 Kelvin. So you're always adding, the 273 is not an exact number. You can Google it, you can go many, many more sig figs, but it really doesn't matter. We'll just go with the 273 because the gnomes will be more precise. All right, so let's just plug in. So we want to plug the T2 in. So this is another thing, and again, I keep saying this because it breaks my heart for 25 years, and it is always the top math students, those of you who are really good with math, that you end up screwing this up because you get too big for your britches. You're like, oh, it's just gas laws. I know how to do this. And so you don't make your list, or you rearrange funny and you end up with T1 times P1. So take the moment. It really doesn't take long to do that. And then the other thing that really drives me crazy, students will make this list. They rearrange carefully because they're like, she emphasized that. And then they plug in wrong. This definitely says T2, and that says T2. So the 318 Kelvin, that's going to go, that's first. You can also cross things off as you use them, because you're only going to use it one time. And then we do our P1, which you can, I didn't specify the unit, so we'll go with 1 ATM. And then my T1 is 273. So I've had, in my other class, a lot of times students will find crossing off helps them. And then you would plug that in and you would get my answer. And if we were in class, by the way, standard pressure is 1 ATM, so we don't look at sig figs for that number. And since my temperatures, once I add the 273, they have 3 sig figs. That is why my answer has 3 sig figs. So if we were in class, I would have you guys go ahead and punch it in. But you can always stop my video later, or you can try these and punch them in, and then if you have a question, you can ask. But I know my answers are right on this because this I've used for so many classes. So last thing I want to do with this one is, does the answer make sense? And absolutely. The temperature increased. So if we increase the temperature, it means more jiggles, more wiggles, so everything's moving. Or you can just say more kinetic energy. But you know, do jiggles or wiggles, let your inner child out. It's kind of what we all need these days. And so you should see a greater pressure, which means more collisions. So if everything's moving around more, you're going to collide into each other. And so I kind of liken high temperature when you give kids a lot of candy. And so people start moving around more chaotically, and so they start running into each other. So that's relationship pressure and temperature. So unless somebody has a question, we're going to move on to Avogadro's law. We're going to look at moles. This is actually where Avogadro's number came from, was what we're going to do on the next page. So I'm going to grab my squid. And all right. All right, Avogadro's law is he studied volume and moles. So just blowing up a balloon is not a chemistry demo at college level. So you got to do something more with the balloon. But blowing up a balloon, as you increase the number of moles, you're of course going to increase the volume, the space needed. So you can think about this as you have more and more kids, you need more and more space. So Janae just inherited 2 kids for tomorrow, and so you do feel like that you need definitely much more space. And where we're gonna go with this eventually, it's on the next page. If we're working with moles, we're gonna be able to use balanced equations and stoichiometry. You guys remember stoichiometry and mole to mole ratios? So Avogadro, he did a whole bunch of experiments, and whenever he had worked with molar mass of different gases, it changed, the volume changed proportionately based on the size of the gases he was working with. And so he came up with this idea of molecules, that they all had the same number of molecules. And people put him down, and it was many years after he died, Einstein actually showed that his idea was correct, which was only like 115 years ago that the term molecules came into existence. All right, so I believe your question says you have 3.14159 grams of helium. That is not moles. Gas laws do not involve mass. You always have to change the mass to moles, which we'll do. And it tells us we have a volume of 765 milliliters. All right, so those two go together. And then it wants to know how many atoms. No, I'm going to make us review everything we learned back in 221 if the new volume is 1.618 liters. So grams you can change to moles, and we can get to atoms from moles. So anytime the question just deals with mass or atoms, you're thinking moles, because using the periodic table, we can change grams and moles back and forth, and using Avogadro's number, we can change atoms and moles. So Avogadro's law, since they are directly related, we would do N1 over V1 equals N2 over V2. So again, when they are directly related, it's always a ratio. The very first law, Boyle's law, was an indirect relationship where one went up, one went down, and so we multiplied. All right, so I am going to be solving for N2 because I'm going to find moles and then change that to atoms. So I'll move my V2, right? So cross multiplying, it ends up on the top. So again, you cannot have a volume times volume or pressure times pressure. And then we'll just plug in. So I'm going to call this roughly my N1 and V1 and my N2 and V2. But again, we have to do a little bit of extra math conversions. So my V2 is where I start, 1.618 liters. And my N1 is 3.14159 grams of helium, but I have to make it moles. It does have to be moles. So your handy dandy, and you still have your hot pink periodic table. I don't. All my hot pink ones are in my office, which I have not been to in a long time. But you would look it up on your periodic table. And if you don't have one, they're online. So that would get me to moles, right? So this is the number from the periodic table for helium. And then I'm dividing by V1, which was 765 milliliters. So before we punch it in our calculator, which I haven't given you time to try that, is you are going to, it's not going to work because my unit here is liters and my unit here is milliliters. So another common mistake I see with students, and again, it's the brightest students because they just take shortcuts, is they move their place value in their head and they don't move it correctly. Now you guys have an advantage because you're at home, so the stress isn't going to be the same as when you're in class and you're doing a quiz and stuff. But there are 1,000 milliliters to a liter. So I'm just in the habit of changing it. And so this is how I set it up and punch it in. And I'm going to actually show one more step here. You can also, and I want to emphasize that, I like doing it all in one setup so I don't have a whole bunch of numbers to deal with. You can also, if this works better for your mind, is if you make a nice list, and again, it's showing your work very nice and neatly. You can also work this part out here and you would get, I don't know, some number of moles. And like here, you can change your milliliters to liters. And again, I do 1,000 milliliters to a liter, but like I know Janae, when we were working on this, it worked better for you to think of it as a milliliter as 1,000th of a liter. And so you get 0.765 liters. Anyway, and then you could punch it all in and you would get to moles, and then you would have one more step. I said, I'm going to show you, I do it all in one setup, but I got here to moles, and then I want to go to atoms, so I would just change my mole to Avogadro's number. So my grams are canceling, my liters are going to cancel, and now I'm getting my moles to cancel. So 1 mole is I wrote that wrong. Avogadro's number of atoms. So if you do break it into steps, you're going to have to number your steps. It is really nice to be able to show it all in one nice flowing setup. And this was a new question that I made up this year. So there is always that possibility that I don't know if I gave you this answer. I have this like penciled in. Please make sure you show the exponent if you use Avogadro's number and that you put your units. You can just say atoms, you can say atoms of helium. But again, if you punch this in and my answer's wrong, that is definitely possible. And then it asks you, does your answer make sense? So again, with these first few pages, I asked that, and then I stopped asking that. But it goes back to this, that we've increased the volume. So we increased the volume, so we're giving it more space. But pressure and temperature are fixed. They're constant. And again, this is key, that the collisions and the giggles are still the same.
Dr. Sherpa, why is it constant again?
Because they didn't change. Okay. And the question it didn't give them. If you start looking at the next ones, we're going to have more variables.
Okay.
So the only things given, and often, oh, it actually tells you that, I think, in this one. It says assume constant P and T. The fact that these are constant is why we can look at this ratio.
But my question to you is, like in the notes, it says assume that it's constant. So it says that, but is there in other problems, am I supposed to generally just know by working out the problem if it's constant or not? Or you're going to say that?
So I would say sometimes I say it and sometimes I just forget, and sometimes I leave it off because it starts getting annoying to put it on every single problem. So if it didn't change, just assume it's constant.
Okay.
If we were being really good and really precise, we would put it with every single question, but it does get to a point where it becomes a little annoying that at the end, it keeps saying that there. So your question is absolutely very valid. It should be there. In your explanations, you do want to include that these two, we can relate them because the other ones are not changing.
Okay.
That makes sense. So that's what I think I was trying to emphasize, that you have more atoms, they're going to take up more space. They have to take up more space because if there's more things there and they're not colliding and they're not jiggling, then they're taking up more space. And that makes sense, just the logic, which gas laws, that's why they're laws, because they're logic and they work. Yeah, question.
Oh, and Ms. Sherpa,
Yeah.
I believe it's cutting off the video, like cuts off right where P and T, where it says P and T constant. I can't see below that. I don't think the camera can go that low. Oh, there we go. Yeah.
Does it show it now?
Yeah, there we go. That's better.
Thank you. Yeah, I don't know why my view this week, last week I could see what you were seeing, and this week I'm not. I know why. I made myself the host in here this time, and that's all the difference. All right, I have to find my rag. Is there a glare, or it's not as bad as last week?
Oh, no, it's fine.
Okay. I know last week when I went back and looked, there was a big glare. So hopefully. All right. So now we're going to combine those laws, those 4 laws. And again, I'm not going to ask you questions about the history, but for those of you who are going to take summer, there's going to be 2 assignments that I'll send out before we go on our break. And one is you're going to write a paper on a famous chemist. You just have to have it approved by me. And so a lot of people will pick one of these guys because they are chemists. Some people will pick somebody who like won a Nobel Prize recently. And another assignment is you're all going to do a chemistry demo. The gas law demos for this term, but you can find another one like a little bit more elaborate. And we'll do them at different times during the term. But those will replace 2 of the labs since I don't know if we'll be able to do anything in the labs. All right, so the combined gas laws is if we take all of those, so P1 times V1, and then pressure and volume, we always had temperature underneath. And I wrote temperature here and N, that you'll always end up, this ratio is going to always be true. So you can now, this is the combined gas law. So it means it combined all those 4 that we just went through into one. And so I tell my students, that's why I have it boxed in. That's really the only one you need. And if you go back to the very first example we did, there was no change. And this is actually back to what Janae had just asked me. Since there was no change in the very first question of moles or temperature, you just leave those guys off. And you have pressure times volume equals pressure times volume. Or, yeah. All right. The other thing is, it says here, the law of inversion. So this is how I presented it with the previous 4 questions. But you can also flip this. So you can also say N1 times T1 over P1 V1 is equal to N2 T2. You don't have to write this down, but you're going to see me do this. It is actually a law in algebra. As long as you flip both sides of the equation, you can do that. And the advantage of this is whatever variable you are solving for, you want that in the numerator. That is probably one of the best hints I can give you. So if you're solving for pressure or volume, you want to have them in the numerator. But if we're solving for moles or temperature, you would want them in the numerator. So, all right, I'm going to erase my second one. We'll walk through these 2 examples. And again, gas laws is pretty much just punching in numbers. So on example 5, make the list. It really helps. So we have 8.65 liters of nitrogen. And I like to write down what it is we're working with. So nitrogen. This is another comment for you. Is remember all those diatomics from Chem 221? So hydrogen, nitrogen, they were all gases. They are still diatomics. So the halogens, fluorine and chlorine, are F2 and Cl2, nitrogen and oxygen and hydrogen. So this I'm going to call my V1. And it tells me I'm at 1.15 ATMs, 35 degrees Celsius. So that's my P1, that's my T1, right? So I just put that bracket, those go together. You have to be careful how the question is worded. They're all in the same sentence. It says of or at, so there'll be a preposition. And then it keeps going. So it wants to know what is the new volume. So that's my question mark. And it gives us a new pressure. And a new temperature. So this is kind of back to the question I think Janae just asked or hinted at. It wasn't directly her question, but this is different from the ones we just did because now we have 3 variables. We have pressure, volume, and temperature. And she was asking, am I going to tell you something's constant? Well, you can see the pressure and the temperature both changed here. The one thing that's not mentioned in the question is it doesn't mention anything about mass or moles or atoms. So I'm going to use this, but I'm going to leave the N off. So it was the question she was asking, are you going to always tell us it's constant? And apparently I don't, because I left it off on this one. So we're going to use the combined gas law. I'm solving for volume. I made my list. So I'm going to do it all in one setup. We are going to have to make the pressures the same unit. I personally always change to ATMs. So if you want, you can change it here. I don't think I did that. Or you can change it up here. That's kind of a preference thing. The temperature you do change, and I don't need to see the math to change it. You can just punch that in, and this is 298. This is T2, and this would be 308. So you're always just adding 273 to get to Kelvin. So again, gas laws do not work unless you're in Kelvin. And actually, you know what, I'm going to show this doing it over here. So I'm going to change my mercury. Again, it's called millimeters of mercury because that's how high the column went. You can also do the change up here and do it all in one setup. But I like doing it in one setup. And I usually see about half of you like that too. And half of you like it to be in your nice list. And then you plug in your numbers so the units are already matching up. Just as long as I can follow your work and it's shown in this nice easy fashion. So this is going to be 0.862 ATMs. Everything is clearly labeled. It makes this really not that bad. All right, again, I can't emphasize this enough. You want to always state the formula, how I've stated it in the notes. You can leave the N out because there's no change in moles. I like to circle, I guess because I'm the teacher, right, to make sure that everybody's following. But it was a student I had who had been a kindergarten teacher showed me this trick like 20 years ago, and I've never gone back to the way I did algebra before, and I was always really good at algebra. That volume, too, which is what we're solving for, has to stay by itself. So I'm going to move the T2, and this is just a cross multiplying. So the T2 is going to move to the top, and the P2 is going to move to the bottom. So it's that cross multiplying. So rearrange and then fill in. And again, it's my top students, the ones who are in calculus, who get really sloppy with their algebra and end up making mistakes. And that would be horrible because you guys are all home now and you don't have the right. It's actually wonderful. I think that's how things should be, because having you take a test is such a false situation, right? All right. So let's go ahead and follow through. Always showing your units. I like to put them in parentheses, but you don't have to. And again, you can cross off. So I'm starting with T2, and then I'm going to P1, and then V1. And again, you can cross off as you use them, because you don't want to use a number twice. If you did, you did something wrong. And then I have my P2, so 0.862 ATMs, and my T1. So stating your formula, plugging in, you have your list, and then you just punch in, and you should get my answer. So again, usually if we were in class, I would obviously pause for 10, 15 minutes, probably because I need to drink water. But you guys can, since we're videotaping, you can go back and try these. And you can always email me, or you can even ask me in office hours. All right. So does your answer make sense? This is actually a much harder question on this one because there's 3 variables. So if we look at the pressure, we see a decrease in pressure, right? We start at 1.15 and we're now at 0.862. And temperature also went down. So what happens to volume? Well, my volume, I see an increase in volume. So temperature went down, but the volume went up. And so it's kind of like, wait, why did that happen? Well, if you look at the change in temperature, it's really proportionately not a very big change in temperature. It's only 10 Kelvin, which is a really small change. The change in pressure is a little bit more. This is, again, back to the question Erin or Janae had asked. I usually, if there are 3 variables, usually there is a dramatic change in one of them, which makes the big change of the one you're solving for. But it is the small change in temperature doesn't accommodate the larger change in pressure, and so volume also changes. So if pressure goes down, volume has to go up. And there is a small change in temperature. And you, of course, would say space collisions. All right, I'm going to move on to number 6, unless you have a question. It's where I also missed 2 boards. We have another piece of the whiteboard, but I could always leave something on the board that you guys could ponder and look at. I guess you can always rewind.
Excuse me, Dr. Sherpa?
Yeah.
So my question is, you said that the problem that we just completed was a combined gas law.
Uh-huh.
So is there one, like a preference of better than the other, or?
No, it's just, so think about, so usually you guys don't have notes when you're doing quizzes and tests. And so rather than learning all the individual laws, I just tell you to learn the combined law. You'll see, actually, as we're doing this problem, this next one, I think I might be able to answer it better. Because I think I anticipate that question every year, and that's why this question's on there. All right. And also question 6 is on there because it's worded different than the first 5. All the other ones, it gave you information, and then the question was at the end. And this one, my question is at the beginning. So I'm making my question T1 because it just says, what is the temperature? And then gives you 5.75 cubic meters. Cubic meters is a volume. So your unknown can be the group 1s or the group 2s. It doesn't matter, just as long as you group them together. Did somebody have a question? Sorry, I heard a...
Well, I was going to ask you about it making sure that it makes sense, but I think I can save that till the end of the lecture, probably, if we're moving
From
on.
the previous one? The previous one's really tough. The change in temperature is so small, it doesn't accommodate the larger change in pressure. I usually ask that question when there's only 2 variables, so it's easier to explain.
Mm-hmm. Okay.
Yeah, but we can look at it again at the end, or even on Thursday.
Mm-hmm. Thank you.
All right, then it gives you a new volume. So I'm going to call that V2. And it gives you a new temperature. And before we do anything, temperatures have to be in, and they all say together, Kelvin. So you would add your 273 and we'd get, what do I get? Oh, I know why. So we get 300, right? It's 27, not 37. Yeah. All right. When you change pressure, I do need to see that step, but the change in temperature, I do not need to see it. So it's just clearly showing our work. All right. Now, this is back to the question Janae had just asked me. So this is more like what will happen like in your homework or your worksheet or on your midterm or whatever, that you'll make your list and now you have to figure out what am I going to do with it. So all I have are temperatures and volumes. So looking at the combined gas law, I mean, rather than making a list of a whole bunch of laws, I'm going to condense this down by the time we get through the next 2 pages to just 3 total laws. And this would be one of them. So I would tell you to have, like for your next midterm, you are going to have a limited amount of time. You're still going to have a generous time, and most students easily get done. And I give you extra time too, because I recognize you're going to have to print it and then upload it and stuff like that. But having like a little sheet. So this is one of them, is you would have, okay, P1, B, this is what's written on your page. You don't need to write this down. T1 equals P2, V2, and 2, T2. Now, back to the question you guys asked. There is no mention of moles, so let's just leave moles off, right? There's also no mention of pressure, so we can just leave pressure off. And we're back to that law. Now, I'm not going to actually write the law like this, and this is the problem, so don't copy this down. You can, but it's going to cause a problem for most of you. The variable we're solving for is T1. And so what students do is they just state the law like this, and then they go, okay, I'm going to move my V1. It has to go down because we cross multiply because we're dealing with fractions. And then they just punch in and solve. And you did not solve for T1. You solved for 1 over T1 because the T1's in the denominator. And so that's what I was trying to say earlier about the law of inversion, that rather than writing how it is, right, we got rid of the pressure and the moles. If you're solving for temperature, because it's in the denominator, before you start rearranging, flip the equation. It's called the law of inversion, so flip it. You have to flip both sides. So the temperature is on top on both sides. It is like the greatest law ever written in algebra. It makes you look like you're a wizard. And they just put fancy names on it. So it's, I don't know if it's actually called the law of inversion. That's what I call it, because when you stand on your head in yoga, it's called an inversion. So you're flipping it upside down. And now I'm solving for T1 this time because that's just how I identified it. So my V1 is going to have to cross multiply over, and it's on the top. And then we would just plug in, and I would leave that for you guys to do. When you get an answer, your answer is going to be in Kelvin. And I want your answer to be in Celsius. So you're going to have some number in Kelvin, blah, 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 blah. How do you get back to Celsius? So
Subtract the 273.
Yeah. So to get to Kelvin, we added. So now we would subtract the 273. And I'm pretty sure you don't get exactly my answer. I think you get like 374 degrees Celsius. Which is fine. If your answers are close enough to mine, usually we're fine. Like on the previous one, I remember in the past some students got 11.3. You should all be getting the same thing though. But I may have actually finally fixed my answer. Usually I'm going to ask you to give the answer in Celsius. You have to solve in Kelvin. So when you plug in, you have to plug in the 300 Kelvin. And then you would change it back. So whatever that number would be. Now this one, when I ask, does it make sense? This one, it is much easier to explain because there's only 2 variables. So if we look, we're moving from, this was 371 degrees Celsius is what we found. So here, going from V2 to V1, I pretty much doubled my volume, right? If you look at the temperature in Celsius, this is a side note, nothing you have to write down. The temperature in Celsius definitely more than doubled, but if you look, if I actually figured it out in Kelvin, it would have been like, what, 640? So as I increase the volume, there's more space. So you go through that whole thing. So you should see an increase in temperature. And it is a proportional increase. So it doubles. There's twice as much space. So you have room for more movement or more jiggles or whatever word you want to use for the chaos that's happening. And then back to the point I was making before is you would want to state that the collisions, which is pressure, and the moles, which is the N, are constant. So I think a better way to answer Janae's question is, even if I don't state it, which I did on this one, that's a miracle, you should still state it in your explanation if I ask you to explain. So the volume and temperature are directly related because nothing else changed. Anyway, that's dealing with 2 or 3 variables at a time. And if you're on Thursday, I'm going to make, we're going to do, yeah, we just have 2 more pages. There's like 4 more pages at the end. And on Thursday, I was going to walk through, there's like 8 problems or 10 problems, and we'll just walk through them together. Or I'll show you the idea of setting them up. The answers are there. And it just requires you to work through them. And when we do that, so what I'm hoping today is you just get a taste for how this works. So you have this idea of temperature and pressure and volume. But again, this is also part of the reason I rearranged the schedule, because gas laws are pretty straightforward because they are laws. I'm going to erase and move on to our next page. I'm just looking at our time. Yeah, we're going to move on because my computer is set to automatically turn off in a half hour. So, all right. So where all this goes is if you rearrange the P1, V1 over N1 is you can get Pivnert. So PV equals nRT, and I know, like Jim studied chemistry before and physics. This is one, when I started teaching 25 years ago, this was one of the few things I still remembered from when I had taken chemistry like 10 years before that or whenever, was PV equals nRT. I mean, moles is the other big thing, but PV equals nRT, yeah, it just sticks with you. And the only new piece is the R. So R is a constant, and we're going to do it with ATMs today, this week. We run into it again when we do kinetics, and we will actually use a different R. So it depends on the units of everything else, but the R that we have, and it's actually on your page, is, sorry, I keep leaving my 0.082057. And of course, somebody always will say, do I have to memorize it? You don't have to memorize anything anymore, which is awesome, maybe. The units of constants are always bizarre. So ATMs times liters per mole K. And it has to do, if we rearrange this, you would have pressure times volume over N times T. And so all those units are in R. This is true in physics. It's one of the things that drives a lot of students crazy in physics, is there's all these constants, because physics is all these mathematical laws, right? And the constants just have to have units to make everything work out. We're going to be doing ATMs. So on the previous problem, I had changed, this was back on example 5, I changed my millimeters of mercury to ATMs. In that problem, because you had two pressures, they just had to be the same units. But as soon as you start using R, which we are for the last like 4 problems that we're going to do here, you have to use ATMs. Your volume has to be in liters. And of course, you're always in K Kelvin. All right. The assumptions, it says on there what assumptions are made. I'm going to actually mention that in the notes on Thursday when I videotape and go over that. So we'll just move on and do the problem solving with this. So question 7 is that you have 0.200 grams of chlorine. And again, from what I said earlier, diatomic, if it's diatomic. So, and we're at STP. So STP means 273 Kelvin, and our pressure is 1 ATM. So again, if I say STP, just realize that's what you have. And the question wants to know what's the volume. So I only have one pressure, I only have one temperature, that's a T. And then I have this, which I can change to moles. So I'm gonna put ... that's gonna be what we change to moles. So we can't use those ratios of P1 V1 equals P2 V2 because I don't have 2 pressures, I don't have 2 volumes. And that's where this formula is great, that there's only one of everything. So we're going to do P equals nRT. Circle your volume. That's the one you're solving for. We're going to divide both sides by pressure. And I know I sound like a broken record, but this happens every time, that it's a student who is just too smart for everybody else and they end up bombing this. The easiest math that you will get to do because they knew it and they rearranged it in their head and it just comes out bizarre. So now we'll just solve. So we have the volume equal. So N is going to be, I'm going to do this all in one setup, the 0.200 grams, but N is not grams, N is moles. And this was chlorine, so you do have to double it. So 70.9 grams to 1 mole. So I'm going to show you a trick. You can just write R, and then temperature is 273, and we would divide by 1 ATM. So like with Avogadro's number, I've told you, you don't have to keep writing 6.022 times 10 to the 23. Same with R. You can just write, it's a capital R. And then those of you who have the really fancy calculators, the 89s and the whatever they're called, the Inspires, this is actually already programmed in your calculator. You just have to be careful because there are several different R's depending on the units. So you would just want to make sure you always pick the right one. You can absolutely write the number in there, or you can just write R. And you would plug it in. Now back to, and our unit when we solve this would be in liters. And somebody always asks me, why did I change it to milliliters? I don't know. So there we go. Since we're on video and most of you aren't here, I can just answer like that. If I ask you to give the volume in milliliters, you of course would change to milliliters. But technically, because the units of R are liters, that answer would be in liters unless I moved my place value and changed it to milliliters. Now back to the question from the previous 6 problems. I would not ask you, does your answer make sense? Because we're not dealing with any ratios here. We're just plugging in and solving. And then I'm not going to walk all the way through 8. You guys can see it still. So the question wants us to find molecules. I wanted to just go through the setup real quick. Molecules is going to get us to, we're going to solve for N. And, right, we have a volume, so the 2.25 liters is our volume. Our temperature is 37 degrees Celsius, which you would just automatically change to 310 Kelvin. And the pressure, 735 torr. So again, there's only one of each piece. So it points PV equals nRT. So the other one that we had was the P1, V1, you don't have to write this down, N1, T1 equals P2, V2 over N2, T2. So we use this one when we're dealing with two of the same, like there were two temperatures given or two pressures given. We're going to use PV equals nRT when there is not. All right, and so for this, I do want to walk through it. I just want to point out a couple of things. I'm not going to plug everything in. State PV equals nRT every time. Again, this is the one that breaks my heart, and it's always somebody who's good at math and they're just being careless. So they're actually not good at math because they're just have an ego. You're solving for molecules. N is moles, so we will have to factor in Avogadro's number. So we're going to have to divide by the R and T. So set it up and you can see exactly how it's going to work. I did one earlier where I changed to ATMs over here. You can do it in the problem, right? So 760 torr to 1 ATM. I like to do it this way. My volume, we're good, 2.25. I'm assuming you guys can see, I just write R and then 310 Kelvin. You can solve for moles, or you can say, okay, well then I'm gonna multiply by Avogadro's number. That's how I like to do it, is to do it in one setup. You can break it into steps, or you can just do it in one flow. And again, I see about half of you will break it into steps, which is fine as long as I can follow your steps. Like on the worksheet tonight, you were all doing beautifully, or you can do it in one setup. And that's just a personality thing. Just in the interest of time, I'm gonna move on unless I did something glaringly wrong. Can I erase 7? All right. And I am confident in my answers, but again, if you are ever watching, for any of you at home watching eventually, and you think you're not sure of something, and actually it's often that, just please send me an email because I make a lot of mistakes. All right. Question number 9 is really awesome because it's chemistry, like everything we've learned all wrapped up into one. And this is really cool. There's a picture of the crash dummy there because this is what, I'm pretty sure this is what is in your airbags in your car. I have not driven, I think, in 2 months. So, which is wonderful. I hardly ever drive anyway, but, and it's a really small amount of this, but what happens, it's a solid, and that is sodium azide. So this ion is N3 with a -1. It's such an unstable, I mean, you should look at that and say, that's just so wrong. That's giving nitrogen a -1/3 oxidation state. And it is, and this is extremely unstable. And so on impact, the airbag in chemical reactions happen in femtoseconds. And the amount of time for your mechanical body to move is more like a second or a couple seconds, and for your neurons to react is a nanosecond. So before you even know that there's been an impact, the gas has already filled up the airbag, and so many lives are saved. So gas laws only work for a gas. So when you have a balanced equation, all those numbers that are given, that you have 25 liters, right? You'd make your list. They have your pressure of 1,000 millimeters of mercury. And that you have your temperature 22 degrees Celsius. All right, so we have a P, a V, and a T, but we don't have any other P's, V's, or T's. So it's pointing towards this formula, PV equals nRT. And the question wants to know how many grams of the sodium azide. So you're going, oh, we'll just do this. PV equals nRT, we'll solve for N. The thing is on this one, you are right. We'll rearrange it again. So PV over RT will equal N. That when you plug these numbers in, you cannot solve for sodium azide, because sodium azide has a little s, and that little s stands for solid. And the theme of today's talk is gas. So PV equals nRT does not work for a solid, except we have a balanced equation that has a gas. So this volume, pressure, and temperature are for nitrogen. So when you plug this in, this is going to give you N, which is going to be the moles of nitrogen. And again, in the interest of time, because I know my computer turns off, it happened to me 2 nights ago. And I find it really funny, because I'm like, oh, well, I guess I have to go to bed. It's the greatest thing. You should all program your computers, your Wi-Fi. It's actually our Wi-Fi is programmed that it turns off for 8 hours. And so nobody can do it. Everybody just has to like read a book, and it's wonderful. Anyway, you find your moles of nitrogen. So I do this as one step, but you can do it as 2 steps. So this would be step 1. You get some number here, blah, blah, blah. And then you guys remember doing this, you change your moles of nitrogen to your moles of sodium azide. It's why we have those koi fish. You guys remember the koi fish? So the coefficients, apparently I say it funny, so it's my New Jersey accent. All right. And then you can go from moles to grams of sodium azide. And you will get my answer. And again, if you break it into steps, make sure I can follow your steps. You could also do this as one long step. And I know my answer is there. I don't know why it says, does your answer make sense? I don't know if yours says that, but mine says, does your answer make sense? Because there's no way you could do that. Oh, it started raining. All right. Oh, we're in good shape. We only have 2 more we're going to do tonight. And I guarantee, well, we're going to do some of these. Again, on Thursday, I'll do more notes, more practice problems, and they'll be mixed up. But I wanted to show you the 3rd equation that we're going to use. And that is PM equals DRT. And so in all honesty, so for my Chem 104, when I teach this, I give them these 3 formulas. So for you guys, because you're at home, what I would do is, yeah, I know what my mistake is. I would just like put those on your periodic table, because really you can do everything with those, and write your R constant. But by the time you do your homework for next Tuesday, you'll actually know these formulas and you'll know your R constant. And you'll be even more brilliant than you already are. I watched this talk, and the guy was like, I want you to turn to the person next to you and introduce yourself as a genius, because you all are. And I was just like, everybody started giggling, but then he like looked at them like, I'm serious. And I'm like, oh, I'm going to use that like my first day of class. And I'm like, well, how can I do that on Zoom? Like, turn to the square next to you. And you can't, everybody's rearranged different on every screen. All right, so PV equals nRT. The thing that's unique about PV equals nRT is the N, which is going to solve for moles or molecules. This one, which is the first one we talked about, that's when we deal with a ratio of 2 volumes or 2 temperatures are given. So PM equals DRT. I'm going to move it over here. This is the same R. This is T in pressure. D stands for density. And gases take up a lot of space. So density is going to be grams per liter. And this capital M stands for molar mass. So I will tell you, I never learned this formula. I never used it for my first like 5 years here. And then Dr. Russell showed me this formula, and I realized, oh, this like makes my life so much easier as a teacher. The advantage of this, and if you're on this page in your notes where it says PM equals DRT in the upper right hand corner, is if the question, like on example 10, if the question point blank says, what is the density? You want to use this formula. Or if the question says, what is the molar mass? So that is where PM equals DRT. In chemistry, like in physics, I've never seen this formula because they don't solve for molar mass. They don't really care about that stuff. And so that's when you would use this. So just a quick review, molar mass is your periodic table. Remember this? So this is grams per mole. That's why it's called molar mass. It's the mass of 1 mole. And so you would state your formula. It's like on number 10. You can write off C. Oh, I'm solving for density. What's the density? So PM equals DRT. PV equals nRT doesn't directly solve for density, but if you have no idea, you can always do everything with PV equals nRT. And then it gives you carbon tetra. So carbon tetrachloride is a carbon with 4 chlorines. And it tells you you're at 714 torr, 125 degrees Celsius. So you would do PM equals DRT. So one last time to emphasize, write the formula and then rearrange, or you're going to do it wrong. I have seen it every time, and so you're going to divide by the RT on both sides. That's kind of up to you. Before you can plug this pressure in, because that's my pressure, that T is for torr, what are you going to have to do to it? Well, if we're using R has the units of ATM, so this has to be changed to ATM. And the temperature, no matter what in gas laws, if you get nothing else out of this hour and a half that we've been together, then that it's awesome it's raining out, and that you should all program your Wi-Fi for other reasons. You're gonna hear me go off on a tangent one of these days on this. You have to change Celsius to Kelvin. And the carbon tetrachloride, you're going to use your periodic table. Remember your beautiful hot pink periodic table and calculate the grams per mole. And that's your molar mass. And then you just plug in and you'll get my answer. And again, I'm not going to walk through it. Density is going to solve for grams per liter. Just real quick, and I'll leave you guys to do 11. I'll answer questions before I move on. Is on number 11, it asks you to solve for molar mass. I wanted to point out, it gives you that you have 4.40 grams and 3.50 liters. So I just put that in as my density, because density is mass per volume. Just, you've got to remember, you have to be in liters when you're working with gases, because of that, and then the other numbers that are given. And when you solve for molar mass, it is grams per mole. And when we're working with gas laws, this is a capital M and it's standing for molar mass. So chemistry has a lot of words that start with an M because of the term molecule. So molecule, moles, molar mass, molecular weight, molecular mass. So it's just keeping it in context. But the one at the bottom of the page I'm going to do on Thursday, just because I don't want to be halfway through and then get kicked out. My cat wants me to feed him too. Do any of you have any questions? We're all good? Thumbs up? All right. I'm going to stop the recording. I did better that time. I asked for questions first.